Hi everyone, my name is Robert Jopier, and today we are going to explore the Swin Transformer, a modern vision architectural design for image classification, specifically fine-grained tasks where subtle details matter, like distinguishing between different cat and dog breeds in our Oxford-IIIT Pet dataset. Unlike traditional vision transformers, Swin uses a hierarchical structure and the swift and shifted windows to efficiently capture both local and global patterns, making it well suited for small datasets without losing accuracy. Let's start by looking at the problem we're trying to solve. Traditional vision transformers are powerful, but they have three big drawbacks. First, they have quadratic complexity, meaning they slow down drastically with high resolution images. Second, they operate at a single scale, so they miss the kind of hierarchical details you'd see in CNNs. And third, they're data hungry. You need massive data sets to get good results, which makes them impractical for smaller datasets like Oxford's Pets. So the real world challenge is how can we design an efficient multi-scale model that works well in resource constrained environments? That leads us to our main research question. Can Swin Transformers architectural improvements translate into strong performance on small datasets like Oxford Pets? Here's a key difference between a standard vision transformer and Swin transformer. On the left, we have traditional vision attention, traditional vision transformer. Attention is globally calculated. Every patch can attend to every other patch. That's powerful if you think about it, but it's also computationally expensive, especially for high resolution images. Swin takes a different approach. It limits attention to small local windows within the image. Then in the next layer, these windows are shifted so that patches get to interact with neighboring regions they couldn't see before. This shift allows information to flow across the whole image over multiple layers, but with far less computation than full global attention. We're using the Oxford Pet dataset, which is a fine-grained classification challenge with 37 different pet breeds. It contains about 7,400 images, but what makes it tricky is the variability. The same breed can appear in very different poses, lighting conditions, and backgrounds. We split the data into 80/20 for training and validation, and resized all the images to either 224 squared or 384 squared, depending on the Swin transformer variant. This resizing ensures a consistent input size while still allowing us to test the impact of resolution on performance. Here's a quick look at some of the Oxford-IIIT Pet dataset images. You can see the diversity within each breed, different lighting, like I said earlier, the pose, the background makes this a fine-grained classification challenge. For example, the same breed can look very different depending on the environment or camera angle, which means our model needs to learn subtle visual cues rather than relying on obvious differences. Before diving into results, let's talk about constraints. We trained on an NVIDIA RTX 4090 with 24 gigabytes of VRAM. Now, in the original Swin paper, they used a massive ImageNet 1K dataset, over 1 million images and 1,000 classes. Our setup is different, smaller dataset, but still computationally demanding. For evaluation, we compared across 4 models. First, vision transformers as our global attention baseline. Second, CNNs, a strong modern convolution database, baseline. Third, EfficientNet, which are scaling optimized CNNs designed for parameter efficiency. And finally, the Swin transformer tested on tiny, small, and base configurations, which use a hierarchical transformer design. This mix lets us compare traditional CNNs, scaling optimized CNNs, standard global attention transformers, and our hierarchical Swin approach. Let's start with the baseline vision transformer. Its architecture uses global self-attention across all image patches, which is powerful but comes with a weakness. It has no built-in inductive bias like CNNs, so it relies on massive data sets to learn. On Oxford-IIIT, this became a problem. It failed to converge. The B16 model failed to converge, getting only about 7% accuracy, and the L16 ran out of memory entirely. Even when it ran, it was about 18 times slower than RegNet. And a few times, my computer had to restart because I ran out of memory, and it was just not efficient at all. The takeaway is that Oxford-IIIT is too small for pure transformer training from scratch. It highlights why hierarchical and more efficient approaches like Swin are worth exploring. And as you could see I have a screenshot of the fifth epoch, and you can see that the L16 was skipped completely, and the accuracy for the second run of my ImageNet, which took forever, was only 4.2, which was lower than the actual 7% I got previously. EfficientNet is built around compound scaling, adjusting depth, width, and resolution in a balanced way to optimize performance. On Oxford-IIIT, the best performer was B3 with an 86% accuracy. Interestingly enough, the larger variants like the B6 and B7 actually underperform. This shows resolution sensitivity. This shows, sorry, resolution sensitivity. Bigger isn't always better, especially on small datasets where overfitting is more likely. The main takeaway here is that scaling rules that work for large datasets like ImageNet don't necessarily transfer to small datasets. And here you could see in the image, this is a screenshot of my EfficientNet benchmark summary. The image size, the method, the params, the flops, the throughput, and the top accuracy for each model. You can see here the B3 topped it with 80.6. We had 75% for B4 and B5. And like I said earlier, the B6 and the B7 underperformed. Our CNN baseline is RegNet, an efficient block structured convolution network. It achieved 84.1% accuracy and had the highest throughput of all models, about 285 images per second. However, we saw clear overfitting with training accuracy at 96%, but validation at only 84%. The takeaway is that while RegNet is a strong and fast baseline, it lacks the global context modeling that Swin transformers bring to the table. So why choose Swin? First, it uses shifted window attention, which keeps computation linear with respect to image size while still capturing local context. Second, its hierarchical design works much like a CNN, building multi-scale features that help with fine-grained recognition. Third, patch merging progressively reduces resolution, allowing deep layers to capture higher level patterns without exploding computational costs. Finally, we leverage transfer learning. Swin was pre-trained on ImageNet 1K and then fine-tuned on Oxford-IIIT, which is essential for getting strong results on smaller data sets. This is a diagram of the Swin architecture. If you look on the left side, just a brief explanation of what's going on. You see the H by W by 3, the 3 channels for RGB. First, it splits into a non-overlapping patches, often 4 by 4 pixels, which then embedded into feature vectors. In stage 1, right here, you see the input of H over 4 times W over 4 times C passes through multiple Swin transformer blocks. Each block uses shifted window attention to capture local context efficiently. In stage 2, the resolution is downsampled by 2. Channels are doubled, another set of Swin transformer blocks. And in stage 3, more blocks for deeper feature extraction. In stage 4, produces the final feature map for classification or downstreaming tasks. The key idea, the model gradually reduces spatial resolution like CNNs while increasing channel depth, enabling multi-scale hierarchical representation. The 2 successive Swin block transformers on the right, basically this part zooms in on what happens inside the Swin transformer block. Each block consists of the first block, the layer norm, window-based multi-head self-attention, residual connection, layer norm MLP, multi-layer perceptron, residual connection, and same as the first, but the attention is shifted window multi-head self-attention in the second block. This shift lets the window overlap across block boundaries, enabling cross-window interaction following LN and MLP again. So basically, this diagram shows the Swin transformer from input image to the final features. Like I explained again, on the left, we start with an image split into a non-overlapping patch and project them into embeddings. That's our stage 1. Each stage contains multiple Swin transformer blocks. Between stages, we use patch merging to reduce spatial resolution while doubling channel depth, similar to how CNNs downsample. Inside each Swin transformer block shown on the right, we have 2 main layers. One uses window-based multi-head self-attention, and the other uses shifted window to let neighboring windows exchange information. Each attention layer is followed by layer normalization, a residual connection, and a multi-layer perceptron. By stacking these stages, Swin builds hierarchical multi-scale features efficient like CNNs. These are the Swin T results, the tiny variant. It's the fastest Swin model, and it offers good trade-off between performance and efficiency. Looking at the loss curve on the left, both training and validation loss drop quickly and stabilize, indicating smooth convergence. On the accuracy curve, we see rapid improvement in the first epoch over here, with validation accuracy plateauing at around 96%. What's important is that the performance gap compared to the larger Swin models is quite small, meaning Swin T delivers the most accuracy at a fraction of the cost. When we move over to the Swin S results, Swin S stands in for small variant, offering more capacity than Swin T. The trade-off is slightly lower speeds, but we get small boosts in accuracy. On the loss plot, we see again a steady decline in both training and validation loss, with validation loss flattening by the second epoch. The accuracy curve shows a sharp rise in the first epoch and gradual improvement afterward, ending at around 95% validation accuracy. Compared to Swin T, the improvement is modest, which suggests diminishing returns from scaling up on this smaller dataset, well, the Oxford-IIIT dataset. Swin B, or the base variant, delivers the highest accuracy of all three. It comes with moderate speed drop compared to Swin T, but it's still much more efficient than the standard VIT, which again didn't really run on our machine. The loss curve shows smooth conversions with very low training loss. By the final epoch, validation accuracy peaks at around 96%, slightly higher than SwinS and SwinT. This confirms the trend. Scaling up in Swin does improve accuracy, but the gains are incremental on small data sets, so efficiency considerations remain important, which is one of the baselines of the research. We're not only looking at the best accuracy, but also in efficiency. And again, this table summarizes our models, the computational cost, the peak validation accuracy. You're starting with the SwinT that gives us 94.93 accuracy with the fastest speed. And Swin S and Swin B edge slightly higher in accuracy at 95.4 and 96, but with more parameters and lower throughput. Interestingly, increasing resolution for Swin B at 384 squared didn't help. It actually led to earlier overfitting. The RegNet 8G variant was a sweet spot hitting around 84% with the best CNN throughput, while scaling up to 16 gigabytes or 16G gave inconsistent results. The EfficientNet model picked with B3 at about 80%. Larger variants underperform, showing diminishing returns on small data sets. And finally, we went over the VIT earlier. It was a complete failure. And again, it may be a result of the hardware limitations on our computer. The key insights or the big takeaways from our experiment. First, Swin dominates. We see an 11 to 16% accuracy boost over the best CNNs. Second, pure vision transformers collapse on small data sets without inductive bias. They simply don't converge. Third, EfficientNet scaling rules from ImageNet don't generalize to small data sets. Fourth, architectural design matters more than just parameter count. Swin's hierarchical approach outperforms much larger models. And finally, pre-training on large datasets like ImageNet is crucial. Without it, none of these transformers would have performed well on the Oxford-IIIT dataset. In terms of hardware impact, our RTX 4090, while powerful, still limited us to smaller batches or batch sizes. Some of the vision transformer failures we saw were due to VRAM bottlenecks rather than just architecture issues. It's worth noting that the original Swin experiment on ImageNet used multi-GPU setups with 48 gigabytes of VRAM, so our single GPU environment is far more constrained. The actual work in that actually worked in our favor for realism. If you think about it, our setup mimics the kinds of hardware limits many real-world deployments would face. And finally, to wrap up, Swin's hacker, my opinion, or based on the research, what I saw, Swin's hierarchical design proved to deliver state-of-the-art performance on small fine-grained data sets like the Oxford-IIIT. So it was a success. We also saw the hardware constraints and not just a side note. They directly shape which models we trained and how efficiently. Transformer learning played a key role, allowing us to achieve high accuracy despite limited data. Overall, our work not only benchmarks Swin against other architectures, but also offers practical insights into the limits and constraints of deploying these models in real-world resource constrained environments. My demos, I ran them separately, locally, using Jupyter Notebook. So first and foremost, this is how I ran the efficient net models. And this is my output, like I said. Same thing for the ResNet model. I ran them locally. This is the output, training per epoch. This is for my Swin B. I ran them separately because initially I was having a few issues because of the different image sizes. I wanted to make sure that the input was not being corrupted and the output that I was receiving was consistent. For the Swin T, um, and this is my Swin small results. This is my Swin tiny results. And the VIT models, the vision transform models, which gave all sorts of problems. So again, my name is Robert Jean-Pierre. This is my presentation on my project. Thank you very much for your time. Have a good evening or have a good day.